Good morning, everyone, and good afternoon. Welcome to the first Roo-ver mission roundup. My name is Ben Sorensen, and I work with EPE Oceania, and it's my wonderful privilege to be the director of the Roo-ver mission and the ELO₂ Consortium. This is our first ever public webinar and the biggest opportunity so far for Australians to see inside the Roo-ver mission that will take Australia's first lunar rover to the moon. So we still have some people joining. I'll share screens. And while people are joining, I would like to acknowledge the traditional owners of the lands on which we meet today. I'm in Brisbane, on the lands of the Yagara and Turrbal people, and we have guests joining from all across our country. So on behalf of us all, I pay our respects to elders past, present and emerging, and acknowledge members of our First Nations peoples that are joining us today as well. So Australia is going to the moon, and this is a national mission. So we really want to ensure that Australians get to see behind the lab doors, to check out the testing facilities, and to meet and hear from Australian engineers and scientists who are making Roo-ver a success. Our journey started in 2023, and a year ago next week, it was that EPE Oceania and our partners in the ELO₂ Consortium were chosen by the Australian Space Agency to deliver the Roo-ver mission for Australia with a funding grant from the Commonwealth. Our mission is to go to the moon and to design, build and test a remotely operated lunar rover on the South Pole on the surface of the moon. We have several objectives, mainly to do that technology demonstration of what Australia can do with that technology. And we'll also be doing technology demonstrations of payloads that will be hosted on Roo-ver. But this isn't our first space endeavour. It's not Australia's first space endeavour by a long shot. Australia has played a key role in supporting international space missions and exploration since the 1960s. Our people and ground-based infrastructure like radio telescopes and communication systems are the key to success of many space missions by many countries. Famously, in 1969, the dish that you see on screen here at Parkes in New South Wales was instrumental in relaying signals from astronauts Neil Armstrong and Buzz Aldrin as they touched down with the Eagle lander on the moon. Australia connected them to the moon with everyone on Earth and relayed humanity's first steps on another celestial body from the Honeysuckle Creek tracking station near Canberra. And today, along with Spain and the United States, Australia operates one of the three legs of the NASA Deep Space Network, performing science with radio and radar astronomy and connecting to space missions, orbiting Earth and exploring beyond our solar system. So the Roo-ver mission is a new step for Australia. It signals an ambition to move beyond our traditional supporting role and into the leadership of our own mission to the moon. It'll be the first time Australia will have operated a robotic platform on a celestial body other than Earth. And it will include Australia supporting the technology demonstration of a NASA payload carried by Roo-ver. Just 7 countries in the world have had rovers on the moon. But these countries are like the United States, India and China. They're all countries with vastly bigger populations with our own. So this is an historic opportunity for Australia. We want to make the most of it, making sure we achieve extraordinary things on the moon and making sure we achieve extraordinary things for Australia on the journey there too. But success with ambitious space missions like this one, that requires recruiting the best people we can to bring to the challenge and building new technologies and capabilities. What often goes unrealised is how fundamental space is to our individual lives and our country's economy, prosperity and security. Almost 1 in 3 Aussies were born overseas. And many of us have family and friends around the world. We stay connected with them by messaging platforms, video and voice calls that are transmitted almost instantaneously via satellites circling the Earth. Tasks as simple as our smartphones, using them to check weather in the morning or getting directions as we travel. They're possible because of space, as is the prosperity we enjoy from international trade and our 2 biggest export industries, resources and agriculture. And since the start of the space race in 1957, when the Soviet Union's Sputnik satellite first orbited the Earth, the technologies that have been developed to go to space have delivered the main benefits to us here on Earth. And those are technologies that improve our lives, like communications and health research, agriculture planning, trade, managing responses to extreme weather events like bushfires and cyclones, even the miniature handheld computers we hold in our smartphones. These are things that improve and enable our lives on Earth, and they're directly linked to the research and development for space. So to remain connected to others around the world and to grow Australia's future prosperity, we've got to have access to space. And space, for us, we've got to be a key part of that international space exploration. And that's a fundamental goal of the Australian Space Agency and the Australian government. And Roo-ver's job is to play a part in that. But safely operating Roo-ver on the moon, it's 384,000 kilometres away, beyond visual line of sight, presents immense challenges. There's at least 1 second of delay in radio signals each way. The environment is unforgiving outside the Earth's atmosphere, with its protection from radiation and extreme temperatures. And the moon's surface, it's an extreme environment. It's dustier and hotter than any Australian desert. It's colder in the shade than winter on top of our highest peak, Mount Kosciuszko, or our coldest mainland point, Charlotte's Pass, or at any of Australia's Antarctic stations. So for Roo-ver to be safe, to survive and thrive in its mission, requires technologies that we develop ourselves here in Australia. And we'll use them for Roo-ver, and we'll apply them to help other Australian industries here on Earth. But beyond technology, it's always about people. And the Roo-ver mission, it's about Australian leadership, ingenuity, teamwork and partnership. In undertaking the challenge of the mission, we'll build Australian capability and capacity, and we'll create new pathways and opportunities for Aussies to be a part of the space industry. They have jobs here in Australia working on this. We've got people in our team who their first job out of university is working on a space mission, and it's wonderful that we're able to offer that opportunity to do that work here in Australia rather than having to go overseas. So I'd like to welcome you to join us, to be together with us on Australia's journey to the moon. We hope you continue to be a part of Team Roo-ver over the next few years as we work towards launch. So now I invite you to hear from some of our Aussie team who will tell us about the challenges of going to the moon and how we are developing new approaches to ensure that the mission is an Australian success. So now I'll pass over to Katie Doyle, who's our technical director for the consortium and leading all of the technical efforts to make this a success.
Hi, thanks, Ben. Yeah, so I'm Katie Doyle from Lunar Outpost Oceania, who are the technical leads on the Roo-ver mission. And I'm the technical director for this incredibly exciting project. I'm here to give you a brief intro on some of the technical challenges we're facing. So imagine a place where it's minus 170 degrees in the shade and over 100 degrees in the sun, where shadows are incredibly long and almost perfectly dark so that you can't really see into them. A place where it takes over a minute to hear back from your nearest neighbour, where the soil is finer than talcum powder and incredibly sharp and wants to stick to everything. Where you have no protection from the radiation constantly bathing you and interfering with your electronics. Then imagine you have to design a small rover, the size of some carry-on luggage, that needs to be able to navigate this landscape while safely carrying a delicate NASA sensing instrument. This is what we're doing on this project. So far, we've spent over 2 years researching this harsh environment, developing and testing prototypes, including building state-of-the-art testing facilities here in Australia. These prototypes have been custom built to test just individual components of our capability that we will need in order to address this harsh environment. We've been trying out new technologies and trying to better understand what the best solutions to these problems are, including involving novel Australian technologies from companies within Australia who may be developing technology for low Earth orbit, and seeing how that can work outside of that space all the way on the moon. Over the next few years before launch, we'll need to do a lot of work. We need to develop and prove our thermal systems, which need to be able to keep us from freezing and overheating, often at the same time, as you get solar heat input on one side, cooking one side of the rover, while the other side is freezing and radiating off into cold space. Our wheels, drive and suspension systems need to be able to cope with the fine dust and rocks without any of that dust interfering with the mechanisms, and making sure that that dust doesn't get kicked up in a way that might be hazardous for the rest of our systems. Our camera and sensor systems need to be able to see and navigate in the harsh lighting environment with that dust involvement as well. So we need to include lighting to illuminate the very dark spaces, but make sure that we don't wash everything out so that everything looks the same. We still need to be able to differentiate a crater from a ridge, and all the fine details there, to be able to see rocks, to be able to avoid them, or understand if we can go over the top of them. Our computers need to make sure we can control everything, and so that the rover can make its own decisions and drive by itself to reduce the impact of any communications delays while not getting damaged by radiation. So we need to be very careful with our component selection and make sure that it's suitable, reliable within that radiation environment. We'll be implementing autonomy on this rover so that it can navigate on its own, to make sure that we are able to do more than just drive, 30 centimeters, stop, wait for someone to review an image, and then make a next decision. We need to be able to drive faster than that in order to navigate the amount of distance that we need to in the time that we have. Our solar panels and batteries need to be able to survive the dust, the heat, the cold, the radiation, and make sure through all of that that there's always enough power for everything else and we don't die due to lack of power. So to address all of these difficult challenges, we're working together as not just one company, but as a consortium of leading Australian companies and researchers and universities. Alone, there's no way any one of us could achieve this. So with that, I'll hand you back to Ben, who'll hand you over to Swinburne and MSL so that they can give you their contributions to this project.
Thanks, Katie. I just want to remind everyone, feel free to drop any questions that you have into the chat, and we will try to answer some of those before the end of the session. So now I'd like to welcome and pass the baton over to Swinburne University of Technology, our partners down there, and Professor Rebecca Allen. Swinburne are a key partner helping the Roo-ver mission deal with some of those environmental challenges that Katie just spoke about. So Rebecca, please take it away.
Good morning and good afternoon, depending on where you're dialing in from. I'm Rebecca Allen, the co-director of Swinburne Space Technology and Industry Institute, and today I'll be giving you a little introduction into the university, but I'd also like to introduce some of our early career researchers that are taking part in this key research. So I have Matt Large and Phil Zanin who are joining me, and they'll be presenting a little bit on some of the specific areas that they're working on. And at the end, I would love to take questions too. If you're just interested in how you could study space, how you can get involved in these cool projects, please drop those questions in the chat. So today, we're just going to give you kind of an overview of what we're doing to support the Roo-ver mission. This is Australia's, as mentioned, Australia's first lunar rover mission, and it's an incredible opportunity for us to get to apply some of our research. So as was done earlier, we always like to acknowledge the country that we're presenting from today. Sky country is such an important element in our space activities, and we're so lucky and fortunate to be building on this incredible legacy community that's really contributed to our culture and appreciation of the night sky. So Swinburne is actually quite a small university. It's small and young, as we say, when we think about the grand scheme of things and universities. But Swinburne has really a legacy when it comes to space, and that's founded in our Center for Astrophysics and Supercomputing. Swinburne has the only partnership outside of the United States with the Keck telescopes. These are some of the most powerful telescopes in the world, and we actually can observe using them without even leaving Hawthorne's campus. We have not one, but two supercomputing facilities, which are helping us lead ground-breaking research in gravitational wave discovery. So that's when two black holes smash into each other, as well as simulating the early universe, but also applying it for key other applications and visualization. So some of you might have even heard of the James Webb Space Telescope and these amazing little things which are called little red dots, but are actually some of the most energetic and distant objects in our universe found in the early data of James Webb. And that some of that research is being led right here in Australia at Swinburne University. So we're able to take this legacy and foundation and expertise in global collaboration to address some of the most fundamental space questions, but then also build on our other legacies in computing and engineering and material science, and really tap into that to try to appreciate how will we help build Australia's space capabilities, and how can we tap into some of these incredible missions and really lead that expertise and that research translation. So only a few years ago, we started the Space Technology and Industry Institute. Now we have 7 core programs which are exploring these key research translations. We have in situ resource utilization, which is all about how when we get to the moon or even taking samples from Mars or asteroids, how can we use that material? How can we understand that material? We also have space robotics, which is about, as you'll see introduced in a minute, is about how we can send technology into space and help it last longer. We have microgravity experimentation, which is one of our programs, which is amazing because we actually have contributions from secondary students where we explore the effects of space and microgravity and send our own payloads there. Complementing this, we have our radiation effects program, which again is all about understanding that extreme environment of space. Now, to understand how we can take our materials expertise and really translate that and thinking about things like sustainable use of outer space, we have our space engineering and manufacturing program. Complementary to that, we have space instrumentation engineering. So when we want to develop this new technology, how will we ensure that when it's in space, it's actually operating as it should? Finally, we have AI for space, which is probably one of our most important areas because it's really about how do we use space to help Earth. So whether that's getting rid of debris and understanding the environment right around Earth in what we call low Earth orbit, or even using space telescopes to look out into space for discoveries, but then also how can we use that same knowledge for looking back down to Earth with Earth observation for things like mitigating climate change and disaster response. The image you see on screen is actually from the terrible bushfire season that we had a few years ago, and Australia is leading some of the methodology to rapidly detect those bushfires. So it all comes from this incredible legacy, but really we have the talent and the power to translate that for the future. So with that said, I'm now going to hand over to our first stream that's helping with the Roo-ver mission. So Matt, please.
Thanks, Rebecca. Hello, everyone. My name is Matt. I'm a postdoctoral research fellow here at Swinburne, and thank you for joining us all here today. I'm going to talk about a bit of my role here at Swinburne and my role for the Roo-ver mission, and that is looking at how radiation might impact Roo-ver and how we can predict and maybe even protect Roo-ver against that radiation. A quick intro to our team here at Swinburne for the Radiation Effects Program. Our director is Associate Professor Jeremy Brown. You've got myself there and Son Hock, 2 postdoctoral research fellows, and then our PhD student Jaden that's helping with this project. So space radiation is quite a risk to our mission success. And it comes in all different shapes and forms. The main ones that we care about when we talk about space radiation are either galactic cosmic rays. So these are charged particles, protons, alpha particles, very heavy ions that come from outside of our solar system and can hit Earth and hit our spacecraft on its way to the moon. Similarly, but from inside our solar system, we have solar particle events. So these are related to solar flares. At any time the sun gets angry and upset, it can spew out all of these charged particles out into space and again hit Roo-ver on its journey to the moon. And lastly, more Earth-focused are the trapped particle belts that we have around Earth, sometimes called the Van Allen belts, some of you may be familiar with. So essentially around Earth, because of our magnetic field, which most of the time shields us from external radiation, it actually does this weird thing and does trap some of those particles very close to Earth's surface. And so as we orbit around Earth and then leave Earth on our way to the moon, it's inevitable that we're going to pass through these belts and experience quite high levels of radiation as we do so. So as I said, the types of radiation and particles that you encounter in space, they vary greatly based on type, based on energy, and based on where you are in your mission. And one thing that we also have to consider that you may not think of is that the moon itself even makes its own radiation field. So as all of this radiation hits the lunar surface and interacts, it can actually scatter back upwards and create a secondary radiation environment that can be sometimes more damaging than the radiation that was originally hitting from above. Now, here at Swinburne, we have two major program streams. We have computational modeling, which is my expertise, where we use the supercomputer that Rebecca introduced earlier and try and model and predict what the radiation might do to our electronics. And then, of course, to support this, we have our experimental testing as well, where we take our electronics to radiation facilities. One of the things we look at these facilities, or an example, is something called a bit flip or a single event upset, where radiation comes through your semiconductor device and can deposit charge in a way that can change the binary state from a 1 to a 0. So this is colloquially known as a bit flip. Sometimes they can do good things. I think the clip that you've just seen here is from the YouTube channel Veritasium, and they cover this concept of space radiation and its effects on electronics very well. So I'd highly recommend watching it if you get the time. But it can be attributed to, I think, the Super Mario Nintendo 64 speed run, a glitch that happened for the person that has the world record. They attribute that to a cosmic ray coming and striking the computer or the electronics inside as they were running it. So sometimes it's not all bad. But for us here today, for our computational modeling, we're mainly looking at two different scenarios. So the first one is the actual launch to the moon, because we can't just sort of take off from Earth and head straight to the moon. Typically on our journey to the moon, we orbit Earth multiple times and we slowly get higher and higher or further and further away from Earth before we do one final burn that sets us off to the moon. And so the way and the number of orbits that we do around Earth dramatically changes the amount of radiation we see. And then, of course, as I mentioned earlier, once we're on the moon itself, these images you see on the right-hand side are some of our computational models of Roo-ver on the lunar surface at the moment. And so we have to model the composition of the moon dirt, the lunar regolith. And sadly, it is not made of cheese. It's made of much harsher stuff that Phil will talk about in a second. But from my point of view, I'm worried about how radiation interacts with the moon cheese and the moon soil and creates more damaging radiation. And then, of course, once our simulations sort of predict what might happen, we then need to go and test what happens in a real world scenario. Now, it's very expensive and very hard to actually send things to space and expose them to radiation. So we typically use whatever Earth-based facilities that we have available. For our electronics, before we actually blast them with radiation, we typically have to remove the protective plastic that is around them. So we use a combination of CT imaging. So if anyone's had an X-ray or a CT scan before, it's very similar to this. We get 3D models of our components, and then we can slowly etch away until we get the exposed silicon chip. And then we take it to a big, angry-looking radiation facility, like you see on the far right-hand side here, and simply put it in the beam, blast it with radiation, and see what happens. So that's pretty much everything from my side and our activities in radiation at Swinburne. I'll pass over now to Phil to talk about what dust mitigation may concern.
Hello, everybody. Thank you for coming. Yeah, so just going to talk a little bit about lunar dust, why it's even a problem. Is there even dust like on the moon? Like, it seems like a very bizarre issue to have. And to investigate this issue, we've got our program lead, Dr. Michelle Dunn, our chief investigator and support, Professor Jeffrey Brooks, a colleague of mine, Daniel Ricardo, and myself, Philip Zanon. And we lead this project looking at lunar dust. So what is lunar dust? It's a very ultra fine grained particles that are very sharp and very angular. The dust portion that we talk about starts roughly about the same size as your red blood cells. They are extraordinarily small and they love to absorb heat. So when you think of like a really black surface that hits the sun, it heats everything up. So back to the issues of keeping the rover hot and cold, it will change a lot of the predicted thermal of the rover when it's deposited. It is also very sharp and abrasive. So that means that when it gets into your mechanisms, it will interlock. The Apollo astronauts had issues even with a telescopic pole that they dropped in the lunar soil by accident. They couldn't extend it anymore. It all locked it into, jammed. And there's also a lot of health issues associated with it, which will be an issue for when we send humans up there eventually. So you can see a SEM image on the right about a lunar, just using simulant, how the structure is just stuck to itself and building up on itself purely because of the electrostatic charges because of this. Now, one of the major issues we're investigating with the Roo-ver mission is how will the dust that is generated from landing deposit onto it, and being able to characterize what those issues are, what the system tolerances are then to be able to deal with it. And then we move on to the operational side of stuff. So on the day side, you get a somewhat positive charge on your particles. And then on the night side, you've got a negative charge. So these are the same sorts of charges, electrostatic charges, that you get when you're unpacking a styrofoam box and all the little nuggets stick to you and you don't quite know why, and they're magnetically, what feels like they're magnetically attracted to you. And that's electrostatic force. And that is primarily the core characteristics of this lunar dust, where it will even levitate because of these charges and then slowly deposit on your rover and your systems. And we look a lot into detail about how bad we expect this problem to be and then implement specific mitigation solutions accordingly. So one of the things we do to test for space is you need to bring space down to Earth because it's very expensive to send something up just for a test. So we have here in the image, and also behind me, is our thermal vacuum chamber, which means we can pull a vacuum and also do those extreme environments, the positive 150 degrees Celsius down to minus 100 degrees, 150 degrees. And we do that using liquid nitrogen, pumping it through the vacuum chamber in special isolator cases and seals. And then we also develop technology. So another big issue of the lunar dust is that we are unable to use traditional methods like cleaning with water. So we have moved to electrodynamic movements and things such as an EDS system, it's called the electrodynamic dust shield. And this is one of our very early prototypes to show what the system could potentially do. And you can see there how slowly over time, and this is a live recording, so it's sped up. You can see that the dust particles are slowly being moved away. Cool. Thank you very much.
Thanks so much. We'll hand it back over to you now, Ben.
Thanks, team at Swinburne. Really appreciate it. And I always find in particular, the dust stuff really fascinating. Now I'd like to introduce Angelo Villarosa, who's the Associate Director of the Melbourne Space Lab at the University of Melbourne. The University of Melbourne and the Melbourne Space Lab team are instrumental in supporting the Roo-ver mission, particularly with understanding the effects of thermal radiation and some of those other challenges. So, Angelo, you have the floor.
Thank you, Ben. Thank you, everybody who's joining online. Just like to echo the traditional owners on the land that we meet here today. So the Melbourne Space Laboratory here at Melbourne University is proud to acknowledge the owners and all of the leaders of past and present generations. So firstly, thanks for the opportunity to briefly present the capabilities that we have here within MSL and what our contribution to the Roo-ver program will be. As Ben mentioned, my name is Angelo. I'm the Associate Director here at MSL Programs. And a bit of what I want to talk to you about today, give you a bit of an introduction on who we are and what we've been doing within the Melbourne Space Laboratory. And then also give you a bit of information about the space missions that we're running at the moment, which are also pretty cool. And then give a bit of extra context on what we're going to be doing in support of the Roo-ver mission. Similarly, we're more than happy to take your questions or to follow up things either after today's call or in the future. A little bit of who we are. So we're a small organization within the University of Melbourne. The team itself is made up of mainly space systems engineering professionals, where we have more than 50 years of experience, combined experience predominantly from European missions. So this is mainly in France, Germany, UK, Spain, where we've worked on and contributed to more than 40 European Space Agency missions. These are Earth observation missions or deep space missions, as well as interplanetary missions as well. The team is also comprised of a group of postdoc researchers and world-renowned astrophysicists, where their main focus is really about researching the origins of the universe, which is also pretty cool. Also working around, or other postdocs working in artificial intelligence, data analytics, your usual suspects, let's say. The team has been working and developing end-to-end space missions here at MSL for the best part of 6 or 7 years. So this includes all of the technical aspects you can imagine of a space mission, from mission conceptualization, design, operation, and obviously finally the disposal of the spacecrafts. We also are managing all of the geopolitical and legal and societal aspects that go along with operating in space. Some of our key competencies that I think is worth mentioning in this presentation is really around our main interest for miniaturizing instrumentation and payloads for spacecraft. So the team has a good heritage and proven capabilities in these areas. And we're also really focused on infrared instrumentation and as I mentioned a bit before, around onboard artificial intelligence and low power computing. We also have, let's say, established a center of competence around thermal engineering and space systems engineering locally here in Australia, which we'll dig into a little bit more today. So this is a bit of a good segue into what we've been working on over the last few years and what we're currently working on at the moment. So the images you see here are from our flagship mission. This is the Spirit mission, which is delivered to the Australian Space Agency as their first and currently only in orbit spacecraft. Melbourne Space Lab was given the honor of conceptualizing this mission, running it from end to end. So we're still currently operating this spacecraft, and it's been in orbit for 650 days. Its second birthday will be only in a few weeks. So you see some pictures here. On the left, you see one of the deployed radiators, which we'll talk about the thermal management system, and Katie and the team from Swinburne also highlighted the complexities around thermal management in space. So you see the thermal radiator that's been deployed here over Madagascar, I believe. The image you see in the middle is looking down at the South Pacific, and we also have, let's say, a nice view of our consortium partners that we built the mission with as well. And then on the right-hand side, again, you see typically for those of you sitting in Melbourne, some cloud over the southeast coast of Australia. The spacecraft itself orbits the planet multiple times a day, and it's been collecting data, as I said, for the best part of 2 years and generating intelligence for our partners. It is a tech demo mission, but we're also now transitioning the operations into something that is almost purely scientific, an institutional mission, if you will. It has its main payload is a really cool box that comes from the Italian Space Agency, where we have deep ties, which is essentially looking to detect energy signals that are out in deep space, which are the results of dying stars. So this is a really interesting research topic, and the team has been collecting some really interesting data that we've been able to build on with our Italian collaborators as well. One of the other things for this particular mission is that we've set it up to be a somewhat risk mitigator for future missions that we've been conceptualizing and that we'll be executing on in the coming years as well, which is also really cool. And again, that will relies heavily on our expertise in the thermal engineering and mission conceptualization aspects that our team has internally. So let's say the segue for what we'll be working on for Roo-ver is really embedded into the Spirit mission, where that magic little box from the Italian Space Agency has some niche operating conditions that it requires in order to work properly. And for this, MSL developed a very specialized cooling system and the associated electronics, which has been critical to ensure that this mission has been a success. And as I said, you can see part of that system in that photo on the left there. When we talk about MSL and Roo-ver, again, Katie and the Swinburne team and Ben have mentioned about the thermal issues that we will see in space. So given that the audience here is probably a little bit diverse, I'd like to maybe just go back to something. I hope I don't break anyone's brains here, but when we start talking about some, let's say, year 8, year 9 physics and science classes, we have a little think about what we mean when we talk about thermal issues or heat. So some of the basic fundamentals, if you allow me to take you back on this little journey, but we want to talk about when things have different temperatures. And when they have different temperatures, heat will transfer from one object to another, and it will go from hot to cold. This is why your parent is yelling at you to close the door when you have the heater on in the winter time. And how heat is transferred from one item to another happens in one of 3 ways. So you have conduction that you see there, which is the transfer between, or the heat transfer when things are touching each other. You have convection that you see in the middle of that pot, which is the transfer of heat when you have a fluid in motion. In this case, it's water, but it could be air, like the heater in your house might work like this. Or the third option there we have here is radiation. So this is the transfer of energy through the electromagnetic spectrum, where you have hotter objects like the sun, which is emitting a lot more than, for example, your gas stove. So thermal engineering is really about understanding how these processes work and then being able to design those technical solutions that are appropriate for the constraints that you find yourself in. Now, these problems have been around for ages, right? So they're problems that need solutions, and these are around us every day. And this could be, like I mentioned before, heating your house during the winter, or the battery inside your mobile phone not overheating, or making sure that your car starts if it's been, submerged in 2 meters of snow, or making sure that your car doesn't overheat when you're driving down the road or driving across the Nullarbor in 40 degrees heat with the aircon on full ball. So now let's take a moment to see how these topics translate and how these problem statements translate when we head out into the vacuum of space. And now I want you to think about the conditions that you might face if you're standing here on the surface of the moon. So unlike the Earth, the moon doesn't have an atmosphere that acts as a radiation insulator. So this means that there's no barrier to help regulate the energy coming from the sun, which is how we end up seeing the really cold temperatures that Katie mentioned before of minus 173 degrees when you're sitting in the shade, or the really hot temperatures when you're sitting in direct sunlight, which goes up to 100, 130 degrees. Now imagine you're this little mate on the surface of the moon, and you have to deal with not only the temperature and the radiative extremes, but then you also have to be able to deal with the conductive issues that are going on inside your body. So this is your batteries being charged up from the solar panels. This is your motors draining your batteries as you're moving from point A to point B across the surface, or the heat that's being generated by the internal electronics that is running your brain and all of your systems. So this doesn't sound so different from the analogies that we just talked about, but I guess you can start to imagine the sort of additional complexities that you start to face when you're trying to design a system for these massive temperature differences and then build it, integrate it, and operate it in these extreme environments, let alone, like was mentioned before, when you're not actually in constant communication with your rover. So these issues, these are some of the issues that we are tackling here at Melbourne Space Lab, and this is where our main focus is on designing the system that allows the rover to operate its mission and to succeed in its mission, and also withstand the extreme environmental conditions that the little rover will be asked to operate in. So this goes not only into the system architecture of the rover and on how it will be handling these extremes and the extreme thermal loads, but also into how the electronics, the circuit boards, the materials will all interact with the space environment so that the rover isn't frozen to death on one side or fried to a crisp on the other. So now I guess the next question is, how will we do this? Well, like most things, we even here on Earth and in problems that you face at home in your everyday life, it becomes a bit of a balancing act, and there's a lot of a balancing act and a lot of smart logic behind it. So that more or less concludes this little brief introduction to Melbourne Space Lab's role on the Roo-ver mission for today, and we hope you walk away from this with a bit of better understanding and appreciation of the extreme environment that your rover is going to have to survive in. And before I go, I just want to bring up this image again that I showed you before, which we captured with our Spirit spacecraft only a few months ago. And you can see in that top right-hand quadrant a little dot. Now, that dot isn't a dead pixel on your screen or some image issue itself. That little marble there is actually the moon. And I think it's a nice, say, holistic, full circle way for us to conclude this little presentation today, because it gives a nice optimistic view of not only where we are at the moment, but where we're going and also where we want to be. So thanks again for your interest. We're happy to take any questions or comments. My name is Angelo, and on behalf of the team here at MSL, and the University of Melbourne, we thank you and we warmly welcome your questions and your feedback. Ben.
Thanks, Angelo. I learn stuff every time I hear you guys speak, so I appreciate it. So thanks for some of the questions that we've had coming in on the chat. We'll run through some of those now. And the first one was from Andrew about infrared. So are we able to use infrared cameras in the shade, or is infrared also shadowed out? So Katie, can you help us with that one?
If I turn my mic on, I can. Yeah, absolutely. So we are investigating the use of infrared cameras. There are different types of technologies of infrared cameras. one that takes up the ambient infrared versus another type of camera that then puts out dots of infrared so it can see what the surface texture is like and get a better understanding of that in 3D. So we're investigating those types of cameras. There is a concern that the infrared coming directly from the sun and bouncing off the surface may interfere with our cameras. So that's a piece of testing that we're looking to do in the near future. But that is definitely an area of technical interest for us that we're looking into.
We'll definitely have some of our other partners that are going to be working on some of those vision systems. They'll be presenting in future Roo-ver Round-ups. So about the design of it, how they're going about that, some of the challenges, but then also the testing and where we test it. So some of our partners that are testing those with us. So thanks, Andrew, and thanks, Katie. There's another one coming up, which is from Mia. Will we be measuring radiation on the moon? This is a question I had actually last night. I was with somebody else, and just how were we going to do it? Or are we just testing the components? Now, I did answer in the chat. We are testing components, not just with simulation, but we will hit them with heavy ion radiation beams so that we can see how they're going to work in representative environments, or at least extreme parts of those representative environments. But Katie, what are we doing for sensing of radiation on the moon?
So we don't have any sensors at the moment, but maybe I can hand over to Swinburne to talk more about the characterization of the radiation environment. So on the engineering side, we've selected components that can meet a certain radiation tolerance, but then Swinburne have been helping us figure out whether that's suitable or not.
Yeah, that's right. Thanks, Katie. Yeah, from a combination of simulations and then experimental tests, like Ben was saying just then, we're going to hopefully get a really accurate idea of how much radiation Roo-ver will get. So it's more of a predictive measure. And we're going to look at the absolute extreme. So, for example, we are currently planning to launch during a solar minimum. Currently, we're in a solar maximum. I think we've actually just had a solar flare last night, or maybe we're going to eventually see some aurora tonight in Tasmania and Melbourne. But we're hopefully launching during solar minimum, which means very unlikely that we'll get intense solar flares. But just on monitoring radiation, one way that we can kind of infer how much dose we've gotten during a mission is we can actually track how some of the electronics on board might degrade or change their operation slightly. And we can match that against how they degraded during tests on Earth. And that will give us an idea of how much radiation we've received at different points in the mission.
Thanks. There was a question from Addy about the size, the dimensions of Roo-ver. Katie, can you tell us a little bit more about, the size, the weight, the characteristics of Roo-ver itself?
Yeah, absolutely. So the size is relatively small, as I said in chat. It's 50 centimeters by 50 centimeters by 40 centimeters that we've been allocated, and that is in consultation with NASA, and it's going to be around 20 kilos in mass as well. There's some other things that we'll have that take up mass as well, other than just the rover. We've got our comms equipment and other interfacing equipment, but we do have to limit ourselves there, and it's really important to minimize our size and mass because it is really expensive to get things up to the moon. I think if you were to contact a commercial, there's quite a few commercial groups now flying to the moon, and you can get commercial payloads directly to the moon from them. I think they charge it out at about $1 million per kilo of payload, which is just so expensive. So trying to keep the mass as low as possible and that size as well within those bounds is really important for the mission. And it's one of the key difficulties on this project too, because we're constantly having to make sure that we're choosing really low mass equipment as well.
Yeah, and we've got to really, because of our constraints, we've got to focus very carefully upon the goals of the mission, what our objectives are, and ensuring that we can achieve those without risking them, and understanding risk and taking on acceptable risk. There were a few questions about payloads. So we do have a payload RFI, which is open at the moment. It's open for another few days. And I put the link in the chat there if you'd like a little bit more information. It's rovermission.com.au/payloads. You can go there and you can get some more information, and you can feel free to propose something. We're really keen to see some of those, but as Katie was saying, keep in mind we're very constrained, particularly on mass. So we're really keen to see what people put in. Tracy had a question about the launch location, Tracy. So we're not sure of the launch location at the moment. We will launch later this decade. We don't have a specific launch date yet. We do have a mission though. So this will be part of a NASA commercial lunar payload services mission called CT4. And it will probably launch from somewhere in America, most likely at this point. We're expecting that. And that's part of the partnership of the Australian Space Agency with NASA in the United States. So we'll find out more about that over the coming months that we'll be able to share. And we'll definitely share that as soon as we've got a green light to give that information out. We'll also be able to talk more about landing sites and other things in future roundups. There were some questions about research papers, and Rebecca, and Angelo, what are you guys doing around research that you're doing through this, and how will you be publishing some of your research?
Yeah, we can jump in first. So a lot of what we'll do will be publishing through traditional research journals. That's a big way that we translate the work that we're doing, as well as presenting it at conferences. Do you guys have specific journals or platforms that you have in mind at this point?
There are journals in mind. I think each specialty within science as well. Like I will most likely publish in a different journal than Phil for his dust research, and then Angelo will for their thermal research. So yeah, probably the traditional methods, as Rebecca said, just scientific journals.
And of course, we'll flag when those papers and everything are coming out. Usually, like ELO₂ and Roo-ver, they'll have press releases. So then you'll know if there's some important kind of results or progress that's been made towards those milestones that we have. Angelo, you probably have some good insight as well.
There's not much really to add. I think you covered it well. In terms of, let's say, the main focus coming out of MSL, we'll obviously be publishing predominantly in the engineering publications, I guess you'd say, the thermal control system and the thermal control units, and the system level engineering that we are performing at the moment. There's a lot of international interest in future missions on this for the time being. So yeah, we'll definitely be publishing. There are some existing papers that have, let's say, a precursor to the work that we have been doing for the Roo-ver mission, and this comes from the heritage that we have on our spacecraft missions, which is publicly available. We can provide those links, and it's good. It's really good reading if that's of interest. So there are publications out there, particularly on the thermal management system that we are, let's say, leveraging for the Roo-ver program, as well as the electronics and the electrical engineering side as well.
Thanks, team. All right, so we'll just go through a couple of other points. Frank and some other teachers and schools on the chat, I'm sure, are interested in what support there is for schools. So the Victorian Space Science Education Centre is part of the ELO₂ Consortium, and they're developing curriculum for teachers with materials to support teachers, help students learn about space, learn about the rover mission to the moon and Roo-ver itself, and some other tools in there to perhaps even plan your own robotic projects. So please feel free to reach out directly to VSEC, so the link's in the chat, and otherwise just reach out to us through socials or to the website, and we can help connect you up. We also have some resources on the rovermission.com.au website under the students link, and there's some things in there which are appropriate for some of the younger ages and a bit up. So some things to get started with, but there will be definitely more of that as we go along. Beltran, Tanaz and others ask questions around internships and other ways to be involved in the Roo-ver mission. At the moment, we do have internships available across the consortium. That's usually on a cycle. So at different times of the year, there will be internships that will be promoted, those opportunities. So I recommend following the social channels that we have for the Roo-ver mission. And you will, and also some of the partner organizations, so like their direct social channels, and you'll find we'll be promoting those internship and other opportunities through there throughout the years. So we do have a few years to go before we'll be on the moon. So there's a few more opportunities to do on that. Also opportunities for collaboration around research. I would suggest perhaps linking up directly with some of the university partners, or also directly with some of us in the industry. So myself at EPE or Katie at Lunar Outpost, Lauren will also be able to help with some of those as well. So where we can, we'll point you in the right direction. We will have the presentation available in future. There was a question, Katie, a technical one, just on how the rover functions, drives on the moon, about its energy and its motors. Do you want to address that one quickly?
Yeah, sure. So we use an electrical power base. So we have solar panels on either side. Since we're at the South Pole, they are on our side, since we always have sun coming in at a very low angle. And then we have our batteries to store that energy and power everything else. So since everything works on electrical energy, there's, little conversion losses there, which is useful for us. Previous, Soviet missions, etc., back in the Apollo days, were using, isotope radiation-based generators. Those are generally not used much these days, except for in much larger rovers, perhaps going to Mars or somewhere like that. So a small rover like this, it's not really a suitable technology for us. And in terms of chemical-based systems, because the mass that needs to get taken up is so expensive, that can also be quite a difficult option, as well as running a combustion engine in space, I imagine would have some difficulties, but I haven't looked into that in that much detail.
Thanks, Katie. We are coming to the close now. We're almost at an hour. So I'd like to thank everyone for joining us today and for all of the questions. I'm sure you've got more questions that you haven't answered. Feel free next time you join, don't be backward in coming forward, throw them all in there. And we'll certainly try to answer them, or even tailor some of the presentation to make sure that we can answer them as we go. I would again just thank Swinburne University, your team, and Angelo at Melbourne, our great partners at Lunar Outpost for their time today. Also the Australian Space Agency and the Commonwealth Government for the $42 million funding that we get. So we've all topped that up with our own monies, but it's what makes this possible for us to have this wonderful privilege to do on behalf of the country. So please, everyone, follow along on the socials. Look out for the next instalment of the Roo-ver Round-up, which will be next year. And we will have links going out there as soon as we set the dates. So I'm expecting it'll be earlier in the new year. And if you've got a payload idea, feel free to submit that, hopefully before Friday. Thanks very much, everyone.